Stanford University.
Welcome to the seminar, People, Computers, and Design. I'm Terry Winograd. I've been having help with doing the seminar this quarter, but I wanted to just take 1 minute on the administrative issues. So this is the last session. Lasts for quite a while. We'll start again in the fall. And if you're taking the course for credit, you should go to the website, hci.stanford.edu/seminar, and look at the page that says Administrative Details, and it will give all the details on how you get credit for the course. Bottom line is if you've come to all of the sessions and signed in, you're done. If you've come to less than all of them, you will need to certify that you've seen the others on video, and if you're doing it remotely for SCPD, you'll need to send something in. The details and all that are on the website, and hope you enjoyed the course. I also want to thank Bree Bunge, who was the TA, helping, unofficial TA, which is even better, volunteer TA, who is the person you want to chase down if you want to find the sign-up sheet and haven't found it during class. And also Lance, who's our technical lead and has made everything work very smoothly this quarter. So thank you all. I will see you next fall. And in the meantime, Scott will introduce our speaker.
Hello, it's my great privilege to introduce Joel Brandt today. Joel's been my PhD student for the last 5 years. And when Joel and I started working together, he's been interested, I think, throughout his entire dissertation in how computers can augment human abilities, very much following in the line of Doug Engelbart's original vision. And what emerged over the couple of projects that we did together before Joel arrived at his dissertation work is I think Joel realized that one of the opportunities that we have in the internet age is for people to share what they know online and for computers to really be a conduit for people to share what they know with each other. And so it becomes that the social web is a way for all of us to augment each other's abilities. And I think it's not accidental that Joel ended up with that as his dissertation topic, because for anybody that's been in my group in any peripheral way over the last 5 years, you'll know that Joel is an incredibly devoted citizen in all of the ways that he's involved in the group. He is the person that picks up the slack whenever anything needs to get done. And I think he's also somebody who has a really incredible work ethic, and his commitment to quality inspires everybody that is around him. When he TA'd my graduate course a couple of years ago, the teaching ratings that quarter were absolutely stratospheric. I think they were the highest that course has ever seen, and there's probably a couple former students from that year in the room today. And you know that it was because of Joel's infectious energy and dedication that really made that course. And I wonder whether, I think several members of Joel's family are here in the audience today, and maybe they can tell me whether part of this is something that's in the water in Iowa. So let's hear about Joel's dissertation.
Thank you so much for that excellent introduction, Scott. And happy birthday, Scott. Thank you for coming on your birthday. And thank you all for coming. So today I'll be talking about the important role that examples play in programming. I'll show that by building interfaces that support example-centric programming, we can help programmers write better code more quickly and ultimately change the way they go about writing code. To motivate this, I'd like to start by presenting a vignette from one of our studies. Jenny was working on building a user interface for a web-based chat room. And while she was staring at this blank text editor window, she said, "Good grief. I don't even remember the syntax for forms." And I think Jenny's here today, and so I'll let you in on the secret that she didn't actually say good grief. Now, Jenny's a great programmer. And if she saw the syntax for HTML forms, she'd know exactly how to use them. In this particular case, she didn't really need to learn anything. She just needed an external memory aid. And web search makes finding this aid very straightforward. So she goes to Google, searches for HTML forms. She clicks on the first result link, and she scrolls on the page, not reading anything, until she finds some example text. She copies and pastes this text and makes just a few typing changes. And in a very short time, she's got a first pass at a user interface. All this took, about 60 seconds, and this is something that would have taken orders of magnitude longer in the days before the web. As this brief example suggests, I believe that the growth of the web is fundamentally changing the way software is built. Specifically, my work is motivated by two changes that are happening in concert. First, the web is greatly increasing the amount of information available to programmers, changing how they write code. For example, hundreds of high-quality tutorials are available in seconds with a web search on basically any technology, meaning that programmers can acquire skills right when they're needed. And second, the web is expanding both access to computation and distribution of the final product, which broadens the space of who writes code. For example, today designers write code to add interactivity to websites, scientists are writing code to run their experiments, and weekend hackers are building the next generation of physical computing devices. In short, the space of who writes code is growing rapidly. To put some numbers to this, Scafidi, Shaw, and Myers recently estimated that by 2012, there would be 13 million people in the United States alone that do programming as part of their job. But only 3 million of these people would be professional full-time programmers. This 13 million, of course, leaves out all the people that program as part of their hobby, and more importantly, leaves out everyone outside of the US. So these two changes present a tremendous opportunity for the next generation of software development tools. The broad goal of my research, then, is to understand how we can best redesign the programming experience to both leverage and amplify the role that the web plays in software development. And to answer this question, we first need to understand people. We need to understand how programmers are using the web today. As such, my research begins with empirical work. We conducted fieldwork and laboratory studies to understand how programmers work today. From this, we generated some hypotheses about how we thought their work could be better supported by computational tools. To test these hypotheses, we built systems that embodied them. We then closed the loop through controlled studies and real-world deployment. And while I think we've built some cool software, I want to stress that my main contribution lies in a better understanding of how to support people's work, not in the technical novelty of these particular systems. Today I'll present 4 empirical studies that address 2 questions. First, how do programmers currently use online resources? And second, how might we design tools that amplify the important role that online resources play? Our first study observed 20 individuals in the lab with the goal of better understanding the range of tasks for which programmers turn to the web. We asked 20 participants to prototype a web-based chat room. Participants were recruited through the Stanford student population, through email lists, and through courses that required research participation. When we were recruiting, we asked that all participants have basic knowledge of PHP, JavaScript, and HTML. However, all but 2 participants rated themselves as novices in at least one of the technologies. Each programming session lasted 2.5 hours, and participants were compensated either $99 in a form of a gift certificate or through course research credit. Participants were allowed to use any resource they wanted while programming, and they were told ahead of time that they could bring books or code or really anything they wanted. One participant did bring code on his laptop. No participants brought any other materials. However, all participants in the study used the web. 3 participants observed each participant, and 1 researcher asked open-ended questions such as, why are you visiting that website, throughout the study to encourage think aloud. We asked the participants to try to meet 5 specifications with their prototype. First, the user of the chat room needed to be able to set their username and post messages. The message update should happen without a page reload. Messages should also have a timestamp. And finally, the chat history should be limited to 10 lines. This last requirement of a 10-line history was somewhat unique and was added so that all participants would need to write some code, even if they began by searching for and installing a complete chat application. Here's one participant's chat room, which met all of the specifications. Indeed, meeting most or all of the specifications was the norm. This table lists 1 subject per line and shows what specifications each subject was able to meet. An unfilled circle means the participants started on the spec but didn't finish it. And as you can see, all participants met most of the specifications, and 13 of the 20 met them all. So as I've said a number of times, in this study, all participants used the web. But how frequently did they do so? The Gantt chart I'm about to show spans the entire length of the study, and will have 1 line for each subject. And participants' web usage will be shown as white bars. Now that's a lot of data. But for the purposes of the talk, there's just a few things I'd like you to get out of this. First, participants used the web a lot, and they used it throughout the course of the study. To put some numbers to this, they spent 19% of their time, about 25 minutes, using the web for on-task information access. This occurred in 18 distinct sessions. And while this data is admittedly anecdotal, all three researchers agreed after the study that there was only one participant that could have even potentially completed the study without using the web as a resource. More interestingly, this participant was not the least frequent user of the web. In fact, he ranked roughly in the middle in terms of amount of web usage. The second thing I'd like you to notice about this graph is that the length of sessions varies greatly. Some last tens of minutes, like the ones I've highlighted here, and some last just seconds, like the ones highlighted here. This high variance in web use duration, even among a single participant, suggests that the web may be playing very different roles in these different sessions. Indeed, when analyzing the data, we found that understanding programmer intention was key to explaining their web use behavior, and thus to designing better tools, which was our ultimate goal. We used our observations to construct a taxonomy. Now, the purpose of our ontological work was to drive design. So the metric for evaluating this taxonomy is simply, does it help us build better tools? We don't claim that this is the one right taxonomy. Other ways of organizing our results might be useful for other goals. So as we compared notes and reviewed video capture data, we found that programmers' usage fell into three categories. First, programmers engaged in just-in-time learning of new skills and approaches. Second, they clarified and extended their existing knowledge to implementation-level details. And third, they delegated their memory to the web, reminding themselves of low-level details right when they were needed. So how do we tell the difference between these different intentions? Well, let's look at an example query from each. A typical learning query looks like Ajax tutorial. While there may be some code-specific terms, like Ajax here, the majority of query terms are English. In these cases, users typically have very little pre-existing knowledge on the topic. This means that it's difficult for them to understand example code without reading text that explains how the code works. In contrast, in clarification uses, the user can immediately understand example code when they find it, even if they couldn't have written that code from scratch. This is what we saw in the vignette I presented at the start of the talk. A typical query is something like JavaScript thread. What's notable about this particular query is that JavaScript doesn't actually contain threads. Here the programmer is trying to adapt her knowledge in one domain to another. With this query, she can easily find a page that explains to her that JavaScript doesn't have threads and gives her an example of how to use timers and set timeout in JavaScript to replicate some thread-like functionality. And finally, in reminder queries, the user typically has almost complete knowledge of how to do the task before they even turn to the web. Sure, they may be missing a few low-level syntactic details, or actually they may just be saving time. Sometimes it's faster to search for and copy 6 lines of code than it is to type those lines by hand. In these cases, we see very specific search terms like fetch_array PHP. Now, let's examine each of these intentions in a little more detail. When participants engaged in just-in-time learning, they often copied and modified code before reading the tutorial's prose. Describing this, one participant said, "There's some stuff in this code that I don't really know what it's doing, but I'll just try it and see what happens." We believe that this participant required how the code works instructions instead of how to do the task instructions, which is what a tutorial typically provides you. So experimenting with and then breaking the code guided a more structured reading of that tutorial. It pointed out what he didn't understand. Next, participants seemed to be interested in only learning enough to complete the task at hand. Describing this, one participant said, "I think it's less expensive for me to just take the first code I find and see how helpful it is at a very high level, as opposed to just reading all these descriptions in text." And finally, participants often learn new terminology from search result snippets. For example, one participant began with the all-English query, update web page without reloading, which as you may recall was one of our specifications. This participant saw the term Ajax in the result snippet, and before clicking on any links, he revised his query to PHP Ajax tutorial. Now let's move on to clarification uses. First, we often saw participants use the web as what you might call a translator. One participant received an error message that read, "XML filtering predicate operator called on incompatible functions." He looked at this and he just mumbled, "What does that mean?" But instead of trying to figure it out, he copied the error message wholesale into his web search window. He immediately found a forum post that said, "This is what you have," followed by his exact line of code, even though he didn't search for it. And "This is what you should have," followed by a corrected line. He copied and pasted it, fixed the bug, and had no idea what the problem was. Similarly, participants would make language analogies to adapt their knowledge in one domain to another domain. One participant said, "Well, Perl has a function to format dates as strings, so PHP must as well." In these uses, participants, as I said earlier, often could not write the required code from scratch, but always knew exactly what the code did when they saw it. Finally, we observed that participants trusted the code they found online in these uses, and often didn't immediately test it. Now, they were usually right to trust it. It was usually correct. But often they would introduce bugs when adapting it, and this would lead to debugging problems later because they believed the code was correct. Finally, as I mentioned, participants used the web as an external memory aid to remind themselves about forgotten details. In some cases, they explicitly chose to avoid memorizing syntax. One participant searched for and immediately copied some code, and we asked him if he'd ever copied it before. He said yes, hundreds of times, and then he went on to say that he never bothered to learn it because he knew it would always be there. In some cases, web search served as what you might call web-enabled autocomplete. If a programmer would forget, for example, the beginning portion of a method name, then standard autocomplete was no help, but web search could quickly recover it. So here the participant forgot the exact name of the MySQL fetch array function in PHP. He searched for PHP fetch array, and the first result snippet contained exactly the information needed. He didn't even need to click on a result. We did observe that despite the utility of these uses, they often broke programmer flow, because the programmer had to shift out of his current working environment and into a separate web browser. So, with a potentially greater understanding of programmers' web tasks, we wondered two things. First, do our findings have ecological validity, or were they simply an artifact of our lab setting? And second, is the structure of a programmer's web search indicative of her intention? That is, do the lexical structure of her query and her page visitation patterns predict her intention? To answer these questions, we conducted a large-scale query log analysis. We obtained 1 month of search and result click logs from Adobe's Community Help Portal, which is a Google custom search engine that indexes Adobe Flex-specific content throughout the web. Flex is the name of a programming framework built by Adobe. Now here's a view of the Community Help search interface. This search engine uses Google's ranking algorithm, uses Google's ranking algorithms, but has a constrained corpus. It only indexes information on Adobe Flex. As you can see, the search interface has an interface very similar to Google. The query log dataset contained over 100,000 queries from approximately 25,000 programmers, and all of these queries were about the Flex framework. For our analysis, queries and result clicks were programmatically grouped into 65,000 sessions. A session was identified as a string of queries and result click data with gaps no larger than 6 minutes. This simple grouping methodology is consistent with previous literature and resulted in 93% accuracy when compared against 300 hand-labeled sessions. After this, we programmatically analyzed 3 properties of each session. First, the format of query strings, that is whether they contain plain English, code-specific terms, or both. Second, the process of query refinement. And third, the types of web pages visited. For example, did they go to tutorials, blogs, API documentation, and so forth. Now, I only have time to present a few high-level results from this study, but for more details on our quantitative analysis, please see our Kai 2009 paper. First, we found that query format predicted the types of pages that users visited. Here, by query format, I mean whether the query contained only English or some code in English or just code. And by pages visited, I mean whether they went to blogs, documentation, or forums. Now, this table presents the types of web pages visited, such as tutorials or forums, broken down by the format. Each column sums to 100%, so the numbers present the percentage of, for example, code-only queries that go to blogs. The maximal value in each row is set in bold type, and all inter-row differences that are bolded are significant at p less than 1,000th using a chi-square test. Now let's look at each row. Adobe API pages were visited primarily as a result of code-only queries. This suggests that API pages are most helpful in reminding situations where participants know exactly what they're looking for. Next, tutorials are most commonly visited by English-only queries. This supports our finding that learning uses from the first study. Participants need tutorials when they only have a high-level description of their problem. And finally, blogs and forums are most often arrived at through queries that contain both English and code. This is because such content is most helpful in clarifying situations, where participants only have some knowledge about specific pieces involved in solving their problem. Second, we found that programmers rarely need to refine their queries. This stacked histogram presents a summary of the amount of query refinement that happens during search sessions. In this graph, the nth bar shows the total number of sessions that have an nth query. So that is, the first bar contains all the sessions, the second bar contains all the sessions that have at least 2 queries, and so forth. Each bar is broken up by the format of the query. And as you can see, this histogram tails off rapidly. To put some numbers to this, there were an average of 1.45 queries per session. This is significantly smaller than for general-purpose web search. Mariam Kamvar and colleagues at Google reported in 2009 that general-purpose web search sessions conducted from the desktop average about 1.94 queries per session. So, despite the fact that refinements are rare, they do still take time. Might we be able to do this automatically in some cases? Well, 31% of the refinements that do occur are done to make the query more specific. That is, the first query is a proper substring of the refined query. When hand inspecting a small subset of these particular refinements, we speculated that a large number of them could have been avoided by leveraging contextual information in the programmer's environment. Specifically, many of these refinements added information like names or version numbers of libraries and frameworks that the programmer is using. The programmer's development environment obviously has access to this information, and with proper tool support, it could be automatically provided to the search engine. Returning to this histogram, let's normalize the height of each bar to 100%. This gives us a view of how query content changes over time. Interestingly, first queries are almost always either code-only or English-only. And as queries are refined, programmers tend to add English. The proportion of English-only queries, on the other hand, tends to remain relatively constant. This suggests that when programmers start off with English queries, they may not know how to make them more precise with code terms, which are an exceptionally precise way to search. So, what does this mean for the way we build tools? First, just-in-time learning is common, and programmers do this learning by experimenting with the code. This suggests that maybe we should be creating tutorials differently. Tutorials should teach how the code works, not how to do a task. And they should perhaps provide a sandbox for users to experiment with the code. Second, we saw that while code written from scratch was almost always immediately tested, code copied is often not immediately tested. To aid debugging, it may be helpful to demarcate copied code, and after each execution of the program, highlight the code that was and wasn't executed. Third, we saw that search was often used as a translator. Perhaps we can automatically extract synonyms and use this to improve ranking. Additionally, perhaps we can automatically search the web for the content of error messages to help the programmer in fixing bugs. Fourth, we saw that programmers often choose to delegate their memory to the web rather than remember low-level syntax. This suggests that we should put search inside the development environment and make current autocomplete tools web-enabled. And fifth, when we saw that participants refined queries, that refinement was often predictable. For example, they would add versions of libraries or frameworks to improve the result set. With the additional context from the development environment, perhaps we could automatically augment queries so that programmers could find good results faster. So, with these insights in mind, and with an understanding of the diverse intentions that programmers have when turning to online resources, we wondered, how can we best amplify the role that the web plays in software creation? Given the diversity of web usage, we believe that there was probably significant value in creating task-specific tools. We chose to first focus on the brief but very frequent uses of the web, those that help programmers clarify their existing knowledge or serve as reminders of implementation-level details. Remember, these rapid sessions, that is, those that lasted under a minute, accounted for well over half of all uses. Now, the main insight behind this decision is that milliseconds matter. Bruleg and other researchers at Google are well aware of the effects of latency in search. For example, an experiment which they conducted increased the number of returned results from 10 to 30. And this change necessarily introduced a 500 millisecond delay due to increased processing. So 500 milliseconds is about this long, right? This delay was largely responsible for the resulting 20% drop in traffic in this population. Amazingly, this effect continues even down to 100 milliseconds. Introducing an artificial delay into the search response with no changes to the UI, just a 100 millisecond delay, causes a 0.2% decrease in the number of searches per user. Now sure, 0.2% may not sound like a lot, but for Google that potentially means billions of dollars in lost revenue. More broadly, O'Hara and Gray's work suggests that small changes in efficiency for common tasks can cause large changes in behavior. We hypothesized that lowering the threshold to complete brief but common web search tasks would do a lot more than just, get the programmer home from work 90 seconds earlier. Instead, it would cause a fundamental change in the way that they use web search. For example, reducing the friction in searching might cause the programmer to search more, or to search for information on problems that they would have avoided or worked around because it was simply too much trouble before. In short, they would write code differently. We began our design work by reviewing video of those brief web sessions from our first study. We immediately noticed a trend. In almost all cases, programmers were looking for example code. So, why might there be this preference for examples? Well, we hypothesized that there are two main reasons for this. Two main reasons that examples are more useful than a written description of how to do the task. First, it may be easier for the programmer to evaluate the quality of information if it is given in the form of a functional example. So in measurable terms, a search result interface which emphasizes the presentation of examples over descriptions may enable users to select a good result faster. Second, it may be easier to transform this information in an example into the next programming action. Again, in measurable terms, a search result interface which emphasizes examples over descriptions may ultimately enable users to write higher quality code because they pick a better starting point. To rephrase these ideas more broadly, we hypothesize that examples have a lower gulf of evaluation and a lower gulf of execution than do written instructions. With this in mind, we wondered, how might we build tools that amplify the role of examples during programming? We chose to first lower the cost of just finding examples. We focused solely on these brief but common uses I mentioned earlier. The tools that programmers use today to search and consume the web are wholly separate from those they use to write code. The web browser and the search engine have no access to the incredible amounts of context in the user's code, despite the fact that code is meant to be read by computers. And similarly, the IDE has no notion of code provenance. It instead assumes that every single character that enters the editor is typed by hand. What benefits might be realized by removing this barrier? To explore this, we built Blueprint, which is a plugin for Adobe's development environment called Flex Builder. Blueprint integrates the web search and code authoring experiences. Let's begin with a scenario that shows how Blueprint works. In this scenario, a programmer would like to write a function that loads some XML data from the web. Here you see the Flex Builder application. Let's zoom in on the code. First, the programmer would like to change the user's cursor to a busy cursor, since retrieving data from the web will take some time. Now, doing this in Flex only requires one line of code, but she doesn't know that line, and she doesn't know the name of the class involved, so standard autocomplete simply can't help her. With Blueprint, she can simply type plain English into her code window. Here she types busy cursor, and then hits a hotkey to bring up the Blueprint search interface. The first result highlights exactly the line of code required, cursormanager.setBusyCursor. It presents this code in the context of a complete example so that she can quickly understand how it's used and get additional information, like the line of code required to remove a busy cursor. Now, this particular example was extracted from an Adobe API documentation page. Blueprint automatically extracts examples from what we call the written web, documentation, blogs, tutorials, and so forth. So, she selects the line she needs and presses enter. It's pasted into her project, and it's basically complete with a comment that tells her where the code came from, should she ever need to revisit it. Now, let's take a look at what this would look like without using Blueprint. The user starts by typing busy cursor into Google. But of course, there's not enough context in this search to yield good results. Luckily, Google's a pretty good search engine, and so it suggests adding a bit more information. She extends the query with autocomplete and performs the search. She then clicks on the first link and waits for the page to load. And finally, is presented with a page that tells her the right method to use, but doesn't make it immediately clear how to call it. After scrolling through several pages of text, she finally finds an example. However, there's no highlighting of her query in this example, so she has to scan the whole thing to find the relevant line, which happens to be right there. Note that this is exactly the same example that Blueprint presented her with immediately. It was extracted from this web page. Now let's go back to the Blueprint scenario. Next, the user wants to load data from the web. She's done this before, and she knows it takes about 20 lines of code to do this. But all she can remember for sure is that one of the main classes involved began with URL. So she types URL into her code, and then she uses standard autocomplete to remind herself of the full class name, URL loader. She selects this and presses enter to paste it into her project. Now she's off to a good start, but she's still a long ways away from the 20 lines of code she needs. With Blueprint, she can simply hit a hotkey and find examples of how to use URL loaders. Blueprint makes it fast to scroll through lots of examples. Just pressing the down arrow quickly takes her to a new example. So she can look through tens of examples in seconds. Rapid access to lots of results is a key part of this task-specific interface. 5 examples down, she finds one that does exactly what she wants. It parses the return data into an XML object, and it has all of the necessary error handling. She pastes this into her code and continues programming. Now let's take a look at the features of the result interface. First, users can initiate queries from their code, or they can type directly into the query box. Each query result has a title, which is taken from the source web page, a short English description, which is automatically extracted, and a link back to the source web page. The user can follow this link without leaving Blueprint if they need additional context. The most prominent feature of the result view is the example code. Query terms are highlighted within the example code to aid scanning the result set. And now let's scroll down in this result shortly. When possible, we also extract a running example, which you can see here. The user can interact with this to see how the code works. Here, this busy cursor example allows the user to click a button that changes their cursor to an hourglass. So now you've seen Blueprint, I'd like to touch on two other ways one might think about addressing this need. Other researchers have worked on creating search interfaces for programmers that address a broader range of programmer needs. Now these interfaces are clearly an important complement to Blueprint. Programmers sometimes want to do things other than find example code. However, we believe that Blueprint succeeds in part because it is focused on exactly one task. This returns us to the milliseconds matter point I made earlier. By reducing friction for a brief but common task, we believed we could qualitatively change the way people work. Second, Blueprint extracts examples from the written web. An alternative would be to extract examples from open source code repositories. This is what, for example, Google Code Search does. We believe that Blueprint offers more useful and adaptable examples because it draws from a corpus that was written to be instructive. That's why they're on the written web. In contrast, production code taken from repositories is likely to have situation-specific details that hinder learning. Now let me give you a brief overview of how Blueprint works. Blueprint consists of three main parts: the client plugin, which provides the interface you saw, the Blueprint server, and an underlying search engine. We use a Google custom search engine, which indexes Adobe Flex-specific content. Query handling begins with the user initiating a query. Here the user searches for chart. The client takes this query and packages it up with contextual information from the programmer's environment, things like languages and framework versions. It then sends the query to the Blueprint server. So here we send up chart, language, Flex3, and some other information. Server uses this query and contextual information to construct an augmented query that is sent to the underlying search engine. So here's something like chart plus Flex3. The search engine then returns a list of URLs to the Blueprint server. Blueprint looks at the contents of all these URLs, that is, looks at the actual web pages, and attempts to extract example code and descriptions from them. This actual parsing and extraction occurs offline and is cached so that we can do this at interactive rates. Once the server has a collection of examples, it formats these examples and combines it with auxiliary information like links to API documentation that is relevant. It sends all of this information back to the client, which visualizes it in the result interface you saw. I want to point out two unique features of our implementation. First, we used a heuristics-based method to identify code on a web page. For each language we want to identify, we manually construct a set of heuristics that match the language closely. These heuristics are things like 80% of the lines must end in semicolons, or at least 3 reserved keywords must appear. Now, an alternative to this approach would be to use a parser for the language we are hoping to identify. If a block of text parses correctly, we know it's a block of code in a particular language. Indeed, it would be easy to achieve essentially 100% precision with this kind of approach. The problem is that recall suffers greatly when using this approach. For example, code on the written web, that is code from tutorials, blogs, and the like, may contain syntactical errors that aid learning, like the one I've highlighted here. This block of code would not properly parse as ActionScript. However, it's a very useful example. In fact, it may be more useful because it doesn't parse properly. A programmer would get a compiler error if they use this example without changing this part. And so they would be required to do so before they used it. After manual tuning, we achieved 88% precision and 88% recall with our extractors. Full details on how this worked can be found in our Kai 2010 paper. Second thing I'd like to point out is that we choose to rely on an existing search engine for indexing and initial ranking. Certainly, this decision comes at a cost. We give up fine-grained control of how queries are processed. However, there are a number of practical benefits for this approach. As I mentioned earlier, speed is a crucial factor in the effectiveness of a search engine. And it's impractical to build a research system that achieves latency on par with Google. Similarly, it's impractical to build a research system that has the same scope and recency as a commercial search engine. Now, I'd like to talk about how we evaluated Blueprint. First, we wanted to understand if example-centric search helps programmers write better code more quickly. Our first study was conducted in the lab with 20 participants. All participants were Adobe employees who used Flex as part of their job. Participants were randomly assigned to one of two conditions. They would either use Blueprint or another search interface that I mentioned earlier called Adobe Community Help. And to remind you about Community Help, it's the same interface you saw earlier, and it's built on top of the same Google custom search engine that Blueprint uses. As you can see, the result interface is nearly identical to standard web search interfaces like Google or Yahoo. The only difference between Google and Community Help is the document collection that it indexes. This search engine only covers Adobe Flex content. So, in this study, and in fact in the study I'll mention next, participants had access to the same document collection in both conditions. And all that varied in this study and the next one is the search interface they used. All participants followed a tutorial task that taught them about the search interface they were assigned, and then they were asked to complete two programming tasks. The first task was directed. They were to load data from the web, as you saw in the scenario I presented earlier, and we asked them to write this code as quickly as possible. The second task was exploratory. They were asked to visualize some weather data in what they believed was the best way possible. Both programming tasks were limited to 10 minutes in length. For both tasks, we measured three things. We recorded the time of first code paste, that is the time to select a useful example, and task completion time. Additionally, we had independent experts rank the quality of what participants produced in each condition. In our directed task, we found that participants selected and copied code significantly faster with Blueprint than with Community Help. Blueprint users averaged 57 seconds to first paste, compared to 121 seconds for Community Help. Task completion time was strongly correlated with time to first paste, which suggests that Blueprint helps people write code faster. Additionally, participants who used Blueprint wrote significantly better code as ranked by an outside expert. Now I'll show you a graph of the rankings of all code. Worst will be on the left and best will be on the right. Blueprint participants will be shown as large circles and control as the small circle. Now as you can see, most Blueprint users fall on the right side of this graph, and this difference is significant at 0.02. Our qualitative observations indicate that Blueprint users wrote better code because they could more easily look over lots of examples, and thus were more likely to select a good starting example. In short, the goals of evaluation and execution were lowered. For the visualization task, all participants used all 10 minutes as they were trying to produce the best design. When those designs were ranked by an outside expert, we found no statistically significant difference in quality. In this case, we did not believe that simply having more subjects would have yielded significant results. Blueprint helps users consider lots of examples, but it doesn't currently help them consider multiple examples at the same time, which may be necessary when users are less sure of the path they want to take. After learning that example-centric search could help programmers write better code more quickly, we wondered if having this tool long-term would cause them to approach the code authoring experience differently. That is, would it qualitatively change how they work? To understand if task-specific interfaces truly change when and how people use search, we deployed Blueprint in the real world. Blueprint was released on the Adobe Labs website and has been deployed for 12 months. We measured adoption and abandonment over this period. During the deployment, we also logged queries and user interface actions such as copy and paste events. After Blueprint had been deployed for 3 months, we conducted a comparative log analysis. We began this analysis by conducting structured interviews with 4 users recruited through a prompt in the interface. Now, one problem with log analysis alone is that it's difficult to know what questions to ask of your data. So the principal purpose of these interviews was to drive the creation of meaningful hypotheses that we could test with our logs. We evaluated these hypotheses by comparing Blueprint logs to Adobe Community Help logs from the same period. At this point, Blueprint logs contain 17,012 queries from 2,024 users, and Community Help logs contain 26,000 queries from 13,000 users. Now I want to remind you that these two interfaces use the same underlying search engine and have the same user populations, so the only difference is the search interface used. Finally, I'd like to note that during these 12 months, both systems were evolving. New features were being added and usability bugs were being fixed. So that makes performing a comparative log analysis for the entire 12 months impractical. However, both interfaces remained unchanged for the 3 months where data was collected for the comparative analysis I'll mention. Perhaps the coarsest metric for judging the quality of a system is adoption. This chart shows the number of new installs of Blueprint per week. We see a great deal of initial excitement where we were advertising and things like that during the first 5 weeks. After that, installation rate levels off to a relatively constant 50 new installs per week. But sure, installation is only one part of adoption. We also need to know whether people are using it once they install it. This graph shows the number of queries issued per week. After the initial excitement period, users consistently conducted about 15,000 queries per week. So are these queries coming from a few power users, or are lots of people using the system each week? Now I'll overlay a graph of the number of unique users per week, and this graph will use the secondary axis you see on the right. Now for the majority of the deployment, these two series track each other closely. This means that throughout the deployment, on average, each active user is conducting roughly the same average number of queries, about 7.5 per week. Now there's an interesting anomaly around week 40. On that week, a new version of Flex Builder was released. Many users installed this new version, but also kept using the old version for their existing projects. So this meant that they had 2 Blueprint installations and thus looked like 2 people. But they still only programmed as much as 1 person programs. So we hypothesized that this is why the number of users appears to double while the rate of searches remains constant. Again, with most any system, it's easy to get a large number of installations simply by having a really good marketing campaign. So we wondered, does Blueprint have a novelty effect? That is, are people installing Blueprint and trying it out for a few days and then giving up? Or are they actually integrating it into their practice? After 200 days, 33% of the top 33% of users had used it for at least 10 days. The top 10% of users had used it for at least 59 days. And the top 1% of users had used it for 151 days. So while some users definitely decided that Blueprint wasn't for them, many users integrated Blueprint into their development practice. Oops, one more thing. I also want to note that these numbers are conservative for 2 reasons. First, Blueprint is a research system, and it doesn't work perfectly in all machine configurations. Specifically, it works substantially better on Macintoshes than on Windows PCs. Second, anytime a user installs a new version of Flex Builder, a beta and things like that, and these are obviously cutting-edge users that are installing labs features, they're counted as a new Blueprint user. For legal reasons, we don't have any way of linking past and current working environments. So now I'd like to move on to the results from our 3-month comparative log analysis. In presenting these results, I'll first offer a high-level hypothesis that arose from our interviews. Then I'll describe how we evaluated that hypothesis using the query logs. First, all of our interviews indicated that the benefits of having this consistent result view substantially outweighed the drawbacks of removing examples from the context of the original web page. Specifically, when asked if additional context of the source web page were necessary, one participant said, "Highlighting of the search term in the code is key. I scroll through the results quickly, and when I find code that has it," everybody away from me is going to miss out on this important portion of the talk. "And when I find code that has it, I can understand the code much faster than I could English." So how might this manifest itself in the logs? Well, broadly speaking, if the context of the source web page were rarely necessary, we'd expect that Blueprint searches would have a significantly lower click-through rate than community help searches, where you have to click through to get the same information. We found that Blueprint users indeed click substantially less, with an average of 0.38 clicks per session versus 1.32 for community help. All statistical results I'll present in this portion of the talk are significant to at least 1,000. Second, all interviewees mentioned that they constructed queries directly from their code. Sometimes query terms came from selecting code they'd written by hand, and other times they would first use autocomplete to find classes or properties of interest, and then use the code generated by autocomplete to initiate a search. In these cases, Blueprint seemed to be working symbiotically with existing code. But how would this manifest itself in the logs? We couldn't log all of the user's actions due to privacy concerns. So one way to look for this behavior is to look for the occurrence of what you might call correctly formatted code. If correctly formatted code is more frequently occurring with Blueprint searches than with community help searches, this suggests that Blueprint is indeed being used in this manner. People are querying with their code. Now we have a unique opportunity. The Flex framework uses camel case for class and method names. That is, internal words of identifiers are capitalized, like cursor manager.setBusyCursor. So looking for these camel case queries gives us a quantitative way to test this hypothesis. Indeed, camel case words appear substantially more frequently in Blueprint queries. Almost half of Blueprint queries, versus only 16.2% of community help queries, contain camel case words. Next, participants indicated that Blueprint was used heavily for task tasks that they were already somewhat knowledgeable about. For example, one participant mentioned that he would often use Blueprint to make sure he wasn't forgetting anything in a 3-step task he did frequently. He would routinely refine the same block of code that reminded him how to set up a transform matrix for the flash stage. In short, he was delegating his memory to the web. He added that Blueprint is perfect for that mid-space between when you don't know what you're doing at all and not needing any help because you know exactly what you're doing. Following these intuitions, we believe that refinding content would be more frequent with a task-specific search interface. When looking at high-frequency users of both interfaces, refinding of information was 57% more frequent with Blueprint's task-specific interface. So, after evaluating these 3 hypotheses, we understood that users were approaching search differently when using a task-specific interface. And we wondered, do users also search for different types of information when using this interface? Well, it's difficult to meaningfully compare the entire space of searches for these 2 interfaces because we have tens of thousands of unique queries in each data set. But what we can do is ask, how do the most common queries compare? We compared the top 50 queries from both interfaces. Now, there's a large amount of overlap in these 2 sets. However, what's interesting is that the relative frequencies of terms are often quite different. One example is for the query alert. Queries for alert were looking for information on how to create a simple pop-up dialog like the one you see here. This query was 100 times more common with Blueprint. Why might this be? Well, alerts are commonly used in debugging interfaces where they're convenient for conveying information to the programmer without forcing her to leave the UI. Sure, there are simpler alternatives like using trace statements or print lines, but they're often less ideal. So let's take a look at the result interface for this query. Blueprint immediately displays and highlights the 1 line of code necessary to display an alert. Using community help, the user would have to switch to their browser, load the search page, search, click on the first result, wait for the page to load, then scroll through several screens of English to find that same line of code. This is one example of how task-specific search interfaces broaden the space of tasks for which search is now a viable tool. Without task-specific search, users may instead be choosing to take suboptimal approaches, here like using trace statements, because the cost of searching isn't worth the benefit. In conclusion, this research brings 2 important principles to light. First, the foregrounding of examples in search results lowers both the goals of evaluation and execution for putting those results to use. Because of this, Blueprint helped users write better code more quickly. And second, task-specific search interfaces can lower the cost of searching in a way that causes qualitative changes in how and when people use search. With Blueprint, for example, users constructed queries in new ways. They queried from their code. They also delegated their memory to the web through increased refining of information. And they began using search for tasks which may have been too small for the amount of effort required with traditional interfaces. In short, when using Blueprint, people program differently. This suggests that task-specific search interfaces can cause a fundamental change in how and when individuals search the web. Moreover, we believe that programmers' increasing reliance on web resources is changing the nature of what it means to be a programmer. In the future, we suggest that programming may become less about knowing how to do a task and more about knowing how to find the right answer. I'd like to conclude today by acknowledging a whole bunch of people that have been instrumental in all of this. First off, my collaborators at both Stanford and Adobe, Philip, William, and Joel. Joel came all the way down here today. It's great to see him. He was instrumental in the first part of this work. Ben and Noah helped with work that we haven't published yet. Vignan is also helping with that work. And Bjorn has been incredibly helpful. He's now off at Berkeley and doing other great things. And of course, my advisor has been exceptionally helpful this whole time. I really appreciate it. Also, everyone at Adobe. Mira has been invaluable, both as a friend and as a researcher. And lots of other folks I've worked with there. I'd like to acknowledge my committee and thank them in advance for the help I know they will provide in preparing a thesis. I am eager for that opportunity. Thank you all for coming today. And finally, I'd like to thank all of my friends and family that have perhaps done the most important part of this PhD, supporting me while I go through it. First, my mother and father, and my brother Eric, who has encouraged me to chased down this discipline of math and computer sciences and things like that all these years. I appreciate everything he's done for me. And Lindsay, who's been incredibly supportive and always there for me during these last 5 years. And now she's off to graduate school, and I hope that I can be a tenth as supportive as she has been over the last 5 years. And also my dog Jake, who most recently helped out with this PhD process by sitting at my feet while I prepared all of these slides. And so you can find out more about this research at this URL, and I'd be happy to take any questions.
So all your work, you rely on Java to implement the code.
I'm sorry?
You also need to use Java
Yes.
to build all your code, right?
Yes, so are you asking what languages this was implemented in, or what languages it works for?
I mean, you most of the time use the Java in your work.
So it depends. I mean, we work in lots of different languages. We've evaluated this right now to be used in the language of the languages that Adobe Flex uses. So that's MXML and ActionScript. I'm not exactly sure what your question is about Java. Are you asking whether these ideas would extend to other languages, or?
No, I mean your work is still based on the Java to extend your work, right?
Yes, yes. So we extended Eclipse. Maybe we can take this question offline if you have more questions about it. Anyone else? Andreas?
You mentioned a couple of times people refining their points on. You never mentioned bookmarks at all, I think. Is that because people didn't have their bookmarks when they were in the experiment?
I think there's a very complicated answer to that question. I think it's a really interesting question. So one thing I would point out, this isn't exactly the same as bookmarks, but this is a more complicated version of the Gantt chart that I showed earlier. And what's notable about the difference here is that all of the web search occurrences are highlighted in orange. So one thing that you'll notice about this is we see lots of uses of the web, not lots, but many uses of the web that don't start with the web search. And this was people browsing to pages they knew existed. So they type in php.net. And we didn't count when they searched php.net, like the actual PHP page. We didn't count that as a web search. So the orange bars are only Google searches. So people definitely, especially in these reminder cases, have resources that they want to go to every time to do this sort of thing. So that sort of gets at your issue of bookmarks. The other way that we've started to address that is we said, well, we had this intuition. Well, wouldn't it be great if when people are using examples, they could bookmark or rate those examples so that they would be more frequently occurring in the future. And so we implemented. I didn't point it out in the interface, but we implemented a ranking feature. Which, I'm sorry. It's probably not particularly important to pull this up, but you see the stars up there in the upper right. And it turns out that I think because of poor UI design, no one used those. So we've had this deployed for, when I checked it last, which was probably 6 months ago, one person had ranked one example. And I think that there's a number of reasons for this. One, it's a lot of effort to go and rank something which we ought to be able to compute automatically. So we can watch if they put the example in their code and keep it around, and that's probably a pretty good indication of whether it was any good. And second, the programmer doesn't really know if an example is good until after they've used it and the interface is gone. So that isn't a complete answer to your question, but I think people definitely do have resources that they want to return to. And I think if we could leverage that in our search interface and use that to adjust rankings and things like that, I think we could do a lot better with rankings.
Going back to your nicely colored version of
Yep, sure.
these profiles. Another way to read that might be, well, gosh, these people are having to flail on the open web for what would be either well-edited learning or reference materials. So perhaps it's an indication of the failure of the tool designers to appropriately make the use of their tools accessible, especially in a multi-tool situation, as all web programming is.
That's a great point. We've had a lot of interesting discussions about this, and I think the answer is it needs to be somewhere in the middle. I think so. In fact, I was sitting down with one of the Flex designers, and he was talking about creating documentation and things like that, and he said, look, there's some things that about any big framework that are just going to be complicated. And if we could get users to sit down and read 5 pages on this, they wouldn't have any problems, right? And they just need to do that. And I think that in some extreme cases, that's definitely the case. That you know, I mean, maybe web search should turn those things up, but that's the way you should be learning those things. But at the same time, you know, there's so many more resources available if you empower the community to create these little bits of documentation. You know, the mapping that says, no dummy, there's no threads in JavaScript. You need to call set timeout. You know, the community can make that mapping and thousands of other mappings like that that just are infeasible to create in sort of a professional context. So I think we need to figure out how to do both of those things really well.
Maybe just one clarification. When you mentioned the written web,
I mean, I guess I'd have to ask you. I guess I'd have to ask you to say to explain what you mean by editing.
Well, like a blog post might be just an offhand.
So
shoot out at the top of the list.
So I think, I mean, we certainly don't want to play arbiters of what is good content and what isn't, and we sort of skirted that issue in this work because Google does want to play that role and is very good at. I mean, they make their money by telling you what is good on the web and what isn't, and we use that as sort of a proxy for what is edited in good content. But that's a great point. I mean, if we didn't rank our examples, if they just occurred randomly, you know, there's lots of bad examples in there too, which is really a problem.
For those of us who are interested and inspired by the research you've done here, what do you think are the most important avenues for future research?
Well, I think there's a couple big ones. So one is one would be I've talked about task-specific search interfaces in one particular domain and for one particular task. And so we've developed a lot of intuitions for this work about how you might build task-specific interfaces for other domains, but we don't know if those results generalize. So I think that's a clear direction that we need to go next. You know, how would you do this? You know, for visual designers. Visual designers use tons of examples while they're working. They use them in very different ways than programmers do. But you know, but this search is a very different problem. It's a visual search task. It's very different. So, you know, what things in our things that we found would generalize to that situation. And you can imagine taking it further afield to other knowledge workers or, you know, really anybody that uses the web. More in line with the domain of programmers, I think there's a lot of interesting questions about how well this works for other languages. So there's a lot of properties of languages that may change how well examples, how useful examples are. For example, you know, we've done this work largely with imperative languages, so ActionScript, which is essentially JavaScript. It might work very differently for declarative languages like HTML. And the great thing about HTML, in fact, it might even work better for HTML because basically any chunk of HTML you take works, right? Like in some sense, it produces some rendering of something, right? You can't really screw it up. You can make syntactical errors, but you can't really make logic errors. And so it might be a lot more useful to work from examples in those situations than imperative languages. And then, you know, I mean, you could think of lots of other you know, languages that don't have large unlined corpuses, like C, you know, older languages that have substantially less than Java and things like that. How would these techniques extend to that sort of thing? So I think those are two avenues for direction. The third thing I'll just say a little bit more about is all we've talked about is finding examples. And there's a lot of stuff that comes after finding examples. So you've got to understand the example, you've got to integrate it, and you've got to adapt it. And then you've got to test it and debug it, right? And so there's a lot more steps there. And I think that that's something that we could provide a lot better tools for. Because as I pointed out early on, you know, right now our editors think that we typed every single line of code by hand, and our debuggers think that we understand every line, even though now people are copying code and trying to understand code that they didn't write and don't even know the person that wrote it. So I think those are three directions we should definitely be going. Yeah?
In this example, did you happen to correlate the rate of success? You know, you said 13 succeeded completely and others succeeded partially in the actual task. Correlate that with the number of minutes, number of uses, number of searches.
That's a really good idea. I think to do that well, we'd also need to have a little bit stronger notion of success than just the how many of the specifications they completed, because you know some people you know, did things like make sure that there were no security errors in their application, or they would handle escape characters correctly, wouldn't have SQL injection, things like that. And that definitely warrants, you know, a higher success criterion than somebody who didn't do that. But I think more to your point, I think the reason that we didn't look into this is that my hunch is the correlation isn't high. So one of the so like I said, the person that did the absolute best job fell about in the middle in terms of web usage. I think he was eighth from the top. And then somebody who, let me see if I can find him on this graph. I think it's this individual right here, who you see used the web a bunch at the beginning and then didn't use it hardly at all. So he was an interesting case. He didn't do a good job in the study at all. He was probably our worst participant. And what he did was he said, I'm going to download Drupal, which is a content management system, a big popular content management system, and download a chat plugin for that, and then modify that to have all of your features. And so he spent a bunch of time on the web initially looking for all these things and selecting one, and that's what he did. And then he got those things installed, and after about where I have my cursor right there, he had 3 of the specifications met because that's what it had that came with it. And then he just spent the rest of the study reading these 50,000 lines of source code that were in Drupal, and he didn't implement anything else. He didn't search the web. He didn't do anything. So I mean, I guess for a variety of reasons, I don't think that the correlation would be high. Sure.
Okay, like your work, you get some kind of budget, like the National Science Foundation or the Army or any kind of government support you, any research fund?
Yes. So I was supported. I was supported by Stanford Graduate Fellowship for several years. I was supported for a short time by a Wallenberg grant, and Adobe has also been incredibly supportive of our work. So thank you, Andreas.
Yeah, so this question comes out of an example. Once I know a language reasonably, I usually try to find out some best practices. So I've been going through this with JavaScript, trying to get the best way to do scope control. Mm-hmm. Okay, so I look at all those examples, and everybody does it a little bit differently, and I wonder, what do you think if I use the tool, whether I would converge more quickly to best practices?
No, I don't think so. I think you raise a great issue. I think this points to 2 things. First, we very much designed for these clarifying and reminding uses in Blueprint. And I think the point you're bringing up is an incredibly important one for being a good programmer, but falls much more on the learning side of the spectrum. So this is something where you're going to need to read people's opinions, read the pros and cons of doing particular things, and stuff like that. And I think that isn't well suited to a very brief interface like Blueprint. But I think one of the things we've talked about doing, so something along the same lines of that is, in Flex, oftentimes there's 2 or 3 different ways to do something. So, for example, you can do event-based programming in Flex, or you can do this variable binding thing that allows you to get around some of the event-based stuff if you just want things to update, right? So these are 2 very different ways of programming user interfaces, and a lot of users will get confused because they'll be doing something one way, they'll be using this data binding thing, and then they'll get examples that are this other way. And so I think it's an interesting open question as to how many of those things we could actually sort of concretize and then use that to divide up the result set. So could we look at your code and say, hey, they're using data binding all over this place. We want to return results that do data binding. Because a lot of times, for the types of things you mentioned, what's the best way to handle scoping? There are sort of these religious camps about different ways to do it. But at the end of the day, I'll go on record, I guess, as saying that what matters most is that you just do it consistently, right? You pick some way of doing things and do it that way. So I think that's definitely one of the things we could do in Blueprint, is try and make sure that people are consistently getting examples that sort of work in the same way. Bree?
Yeah, what do you think are the implications of using code but you don't know how it works and you're just plugging it in?
I think that's a great question. We had actually a really long debate about this in my thesis proposal, and I think I think the first thing I would say about it is that I think it's great because I think people learn by example, and so sure, it's problematic that you're using code that you don't know how it works, but you want to do a task that you don't know how to do. So at some point, you're going to have to work with something that you don't understand. And working with examples really gives you a very close mapping to what's actually going on under the hood, rather than just sitting down at your desk and reading a book about how to do it and then trying to do it. The second thing I would say is that what we ended up talking about in my thesis proposal was, should we actually be trying to do anything to teach people to do things a better way? And I think there's a huge amount of research to be done in interfaces that teach people, but I don't really think It's our place to say what's good and what's bad. This is something that people are doing, and if we can support it better and fix errors that happen when they do it, then that's a good thing. So one feature of, so for example, one of the problems with blindly using example code that you don't know that well is if it's got some bug, like a security error, you're not going to know about that bug. You won't test for it, and you might inject bugs into your own code, right? So this is a bad thing. But people are already copying and pasting code, and so this is already a problem. And what we do in Blueprint is, you didn't see this in the demo, but when you paste code from Blueprint, we also paste in this unique identifier that says, that tells our server, or that maps on our server to the exact example you pasted. And so if you leave that unique ID in your code, every time you open that file, we send that unique ID. We don't send your code, but just that unique ID off to the server and say, have any of these examples that you pasted been updated? And so if somebody fixed a bug, whether it was a security error or whatever, we can prompt the user and say, hey, this example changed. And we can't tell you why. That's equivalent to solving the halting problem. But we can tell you that it changed, and we can show you the before and after. And so this improves the situation that was already happening, people copying bad code. Yeah, Eric.
I think actually you spoke to that a lot just now, but question, you touched a little on what improved code quality, but as far as code maintainability, as well as the maintenance process of code that's created this way. Do you have any information on that or future work on that?
Lots of people have we didn't study that, but it's a great question. Lots of people have studied and tried to produce better interfaces for dealing with code clones. That research mostly falls in the software engineering community, where code clones happen throughout a really big project. And there's been a lot of work on how to help people, how to actually, so for a long time the software engineering community said, it's really terrible to copy and paste your code. It's a bad thing. And then they sort of had the same observation as I was just mentioning to Bree, that people are doing it anyway, so we ought to support it. And so there's research refactoring systems that allow you to just go and blindly copy code like you want to when you're working these big systems, and then after the fact go back and refactor those really well. So tracking all those things. So hopefully that addresses your question. Yeah.
Are you working in Adobe? You are the worker?
I was an intern at Adobe for about 1.5 years, and I will be joining them actually in about 3 months.
They have a kind of work schedule in the older employee in the Adobe. They work a long hour from 8 in the morning and until 11 or something. I think Adobe have a good achievement. They have many products. And what work situation in Adobe is.
Hopefully they won't make me work too hard. We'll have to see.
We have done that here.
Any other questions? Thank you.
For more, please visit us at stanford.edu.